Hi, imagine you are playing a sports video game with your best friend. Now imagine this friend has much less experience with that type of game than you, and you end up winning every match with a huge margin. That doesn't sound like fun, right? You'd probably feel unchallenged and bored, while your friend would simply feel frustrated. To tackle this issue, some games include player balancing mechanics. These mechanics allow players who lag behind to catch up, usually by giving advantages to them or by providing additional obstacles to the high-performing players. For instance, in a sports game, reducing the accuracy and the speed of the players on the winning team. But how are these perceived by players and how do they affect the experience? I'm Gonçalves from the University of Lisbon, and I'm here talking on behalf of my colleagues Daniel, Pedro, João, Tiago and André. And in this video I'm presenting the trick is to stay behind, defining and exploring the design space of player balancing mechanics. Mismatched skills and expertise in gaming contexts can have a significant impact. Players may end up frustrated for not being able to keep up with other players, or in turn feeling unchallenged when outperforming. Past approaches aim at tackling this issue. One approach is to use matchmaking systems to group players of equivalent skill levels. However, these are usually inaccurate in determining players' actual skill, and more importantly, matchmaking is not a solution for friends and family with disparate skills that want to play together. Some games apply changes to the gameplay to bring players closer in performance. Some popular examples include providing aim assistance in shooting games or increasing the speed of players behind in racing games. Past research has explored different implementations of balancing by manipulating certain design aspects, such as if the change in the gameplay is visible, the timing of the effect, and if it depends on player input or not. This work shows that player experience and perceptions toward balancing greatly vary according to how it is implemented. And to understand comprehensively the impact of such design choices, it is important to develop a shared understanding of the design space of player balancing. Previously, Baldwin and colleagues proposed a framework to formalize this design space. However, some dimensions found to be relevant in past research were not fully captured, such as determination at different levels, as discussed by Johnson and Grönbach, or the distinction between handicaps and boosts, as made by Rogers and colleagues. As such, in this work, we make a twofold contribution. First, we propose a design space for player balancing mechanics, capturing aspects that were not formalized before. Second, we report on a mixed method study focused on the effect of two subcategories of our design space, targeting direction and effect dependency on skill. Now, delving into the first, the design space of player balancing mechanics. To build this design space, we leveraged the framework proposed by Baldwin and colleagues and expanded it with further design possibilities by scrutinizing related research, discussing balancing mechanics in commercial games, and relying on our own experiences as regular gamers. Through regular meetings, we gradually developed its structure, with each new version improving in the clarity of definition and distinction between concepts. Its final structure comprises 6 categories. Determination, which refers to who or what makes the decisions that dictate how the mechanic should function. Timing, which refers to the circumstances that trigger the effect of the mechanic, its duration and termination. Targeting, referring to the subjects whose gameplay is affected by the balancing mechanic. Effect, which consists of the actual changes made to the gameplay and the objective impact they have on players' performance. Feedback, which refers to the way the mechanic is conveyed in the gameplay through visuals, audio, and other modalities. And finally, information, which refers to the type of data that is used to dictate if and how the mechanic should be applied. I will not go over each of them, obviously, but I want to note that we provide extended definitions and multiple examples for each category and subcategory. We also offer recommendations of use and potential applications, which range from a tool to inform study design and analysis to a shared language that supports ideation and communication. As a second step of this work, we aim to operationalize our design space to explore specific permutations and better understand their effects on player perceptions through a user study. We focused on 2 subcategories. Direction, which is a subcategory inside targeting, and captures which side is affected by the balancing mechanic. Either the low-performing players are assisted or the high-performing ones are hindered. In some cases, the mechanic affects both sides. For instance, in Mario Party, there is a negative event where Bowser takes coins or points from players. However, if a player has no points, Bowser gives them a certain amount of pity coins. This mechanic assists low-performing players so they have an opportunity to catch up with stronger players, and this is not the case, but if Bowser would take more points from those who were on the lead, this mechanic would also hinder high-performing players. The second subcategory is dependency on skill, within the effect category, indicating how much the effect is dependent on the skill of the players. To give an example, in Mario Kart, players can use shells to hit opponents, where the most powerful shells are usually given to players behind. Green shells need to be thrown with accuracy, and as such have a high dependency on skill. While red shells, given to players behind, automatically target players in front and have much lower dependency on skill. We developed a competitive racing game with 7 player balancing mechanics that result from manipulating these two subcategories into different combinations. It consists of a simple racing game where each player controls a penguin going down an ice track, trying to dodge various obstacles and cross the finish line first. Our 7 balancing mechanics are: first, the boost with invincibility, which gives a speed boost to a player for some seconds with a shield that allows them to ignore obstacles. This is an assisting mechanic with low dependency on skill. The boost without invincibility, which had the same speed boost but it didn't have the shield, with players still having to dodge obstacles. In this case, it's an assisting mechanic with high dependency on skill. Then the obstacle reduction, which removes the number of obstacles for the player behind. It's an assisting mechanic with high dependency on skill. And the obstacle addition, which added obstacles for the player in front. This is an hindering mechanic with high dependency on skill. Then, the wall with a tunnel, which is a new type of obstacle added to players in front. It is a hindering mechanic with a high dependency on skill, as players can pass through the tunnel if they have enough skill. The timed gate entirely blocks the passage, with the player having to stop and wait until the gate opens. This is an hindering mechanic with low dependency on skill. And finally, the forced handbrake, which is a sudden decrease of speed suffered by the player in front. It's also a hindering mechanic with low dependency on skill. Using the game as our research instrument, we conducted a user study aiming to answer the following research questions. First, how do players currently view and embrace player balancing mechanics in multiplayer games? And second, what is the impact of targeting direction and effect dependency on skill in players' perceptions of enjoyment, fairness, and effectiveness in the competitive multiplayer experience? We recruited 8 pairs of participants with ages ranging from 22 to 29 and varying levels of gaming expertise. All pairs were friends. The procedure for all pairs was as follows. First, they played a series of races, side by side on the same laptop, experiencing all the 7 balancing mechanics. They then filled a questionnaire individually on the computer, which included a validated scale to assess player experience, the mini PXI, and ratings for each balancing mechanic in terms of enjoyment, effectiveness, and fairness. Finally, they took part in an interview together as a pair. Our analysis is centered on the qualitative data, which we analyzed following a codebook thematic analysis, combining a structured coding procedure and reflective interpretation. Our results revolve around 6 themes. Yet, in this video, I will focus on 2, which detail how targeting direction and effect dependency on skill affected player experience and perceptions toward balancing. Our remaining themes detail experiences of skill disparity in gaming, acceptance of balancing dependent on context, the importance of naturalness, prominence, and transparency, and the fine-tuning and dynamic application of balancing. So first, how did targeting direction affect the experience? In participants' answers, there was no consensus of preference for assisting or hindering mechanics, with both having advantages according to them. Some participants were vocal about their perceived unfairness of hindering mechanics. These participants justified their perspective by highlighting they felt it was unfair to penalize a good performance. Such negative reactions may come from the fact that players do not feel rewarded when performing well and instead feel punished when participants stated. Those who have skill do not feel that they should be better because they will end up having some kind of handicap. There were also participants that highlighted the other side of the coin. They felt that assisting mechanics were just making the game easier and made them feel less achieved for that. Some just wanted to improve their performance by themselves without those changes to the gameplay. As such, many preferred hindering mechanics, as they increase the difficulty level for high-performing players and prevent them from getting bored. For instance, a participant said, "Hindering is even more fun, because I felt a little more adrenaline, like he's right there following me." Now, delving into the second theme I'm going to talk in this video. How did dependency on skill affect the experience? Almost all participants, with a few exceptions, expressed their preference toward mechanics that somehow depend on skill, to ensure fairness and merit in the competition. This preference was especially manifested for hindering mechanics, with participants expressing their discontent with the timed gate and the forced handbrake. These mechanics force the player in front to decelerate without any chance to avoid a negative effect on their performance. A participant said, "I don't like this type of balancing because you're blocking the person and they cannot get out of there, regardless of the skill she has." Some participants defended that hindering mechanics should provide additional challenges but still provide the opportunity to deal with them, either mitigating their negative effect or completely avoiding it. The same was highlighted for assisting mechanics. These were considered fairer when they provided an opportunity for low-performing players to catch up, depending on how well they leverage the benefit. Now, concluding, this work constitutes one more step in how we formalize, design, and understand player balancing in gaming. We first present a design space, grounded in related research and examples from the industry, with potential applications in analysis, ideation, study design, and clearer discourse. We then present the results of a mixed method study focused on exploring how targeting direction and effect dependency on skill, two subcategories of our design space, affect self-perceived enjoyment, fairness, and balancing effectiveness. Further research is needed to understand the effects of other subcategories, taking into account factors inherent to the game genre and context of play. We hope our results contribute to more inclusive multiplayer experiences where skill disparity is considered and embraced by design. Thank you very much for your attention.